We have discussed how to change the priority of a process in a previous video. Here, we discuss how to implement a very simple priority scheduling policy in xv6. First, let's see how xv6 does scheduling. It starts from main, which is in main.c. So when it boots, it does the initialization, and at the end it calls mp-main to finish the processor setup. mp-main is here, and it does the initialization, and at the end it calls scheduler. This function never returns, as you will see. This is in pro.c. This is the scheduler function. It does the scheduling of the processes. It has an infinite loop, so it hangs forever, and it loops through the process table to search an entry that is vulnerable, to search for a process that is vulnerable. If it is not vulnerable, it continues to search. When it finds one, then it will switch to that process. So it set the state to running, and it executes this switch statement. This function, what this function does is that it saves the current registers in the CPU scheduler. This is actually a pointer points to a struct context. This is the struct context. You can save the values of the registers, including the instruction pointer, and then it loads the registers from the process context, from P context. So that means the instruction pointer will now point to the newly loaded process, and we start executing there. Then when the instruction pointer returns to here, well, when the process exits or terminates, or when its quantum expires. Its quantum expires when the timer generates an interrupt. The interrupt will cause a system call to call trap, which is in trap.c. This is the function trap.c, and if the trap is generated by the timer interrupt, then execute this statement. If pro is non-zero, post state equals running, and the trapped number is the timer, then it executes yield. Now let's see what does yield do. Yield is in pro.c. So yield basically reset the process state to a vulnerable, and then execute sched. And let's see what does sched do. This is a sched function, and what it does is that it basically saves the process context. Then save the current instruction pointer and other registers into this struct, and then it loads the CPU scheduler's context back to the registers. So that means the instruction pointer will point to where it was saved, so it should be back to here. So it means it comes back to here, and then it is basically done, and set the approach to 0, and look for another process to run. Okay. If it has gone through the whole table, then it will release the lock, but it will go back to this loop, and it will acquire the lock again and go through this table again. So that's how the scheduler works. So this is a round-robin scheduling. Now suppose we want to implement a priority scheduling policy. So what we does is that we want to pick a process that has the highest priority to run all the time. Okay. Now to do that, first we will set the default priority of a process to 10. Okay. And we do this in pro.c. We do this in prod. Okay. So when it is created, we set the priority to 10. So that's the default priority. And in our notation, as we discussed in the previous video, the lower the value, the higher the priority. And to make things simple, we just limit our number of CPUs to 2, so that we won't get confused when we do the test. And also, if a process is loaded via exec from the shell, then we give it a higher priority, and we give its priority to be free, so that we can execute shell command with high priority. And let's see how we implement the policy. We just modify the scheduler. So we add another struct pointer. Again, these are the same. And we define another pointer called high P, means a pointer pointing to the high priority process. Is set to new. We define new to be 0, basically. And again, we iterate through the table. And again, if the state of the process is not runnable, we continue, look for another one. If we find one that's runnable, then we set high P to P to be point to that process. And we compare this process with all the processes in the table, and of course we try to compare those that are runnable. If not runnable, we continue. And if we found one in the table that has high priority, that means smaller value, then we set high P to that one, that new process. So that means we will pick one that has the highest priority eventually. And then when exit is snooped, high P will point to the process with highest priority. So now we let P point to high P, and pro points to P, and again set the state to be running. And again we use switch to run that process. And at the end, when the quantum expires, that process will be changed back to runnable, will be put back in the table. And again, if no other process with high priority has come, that process will be picked again. Okay. if some other process with higher priority has arrived, then the higher priority process will be picked. Okay. So by doing this, the process with highest priority will always be picked to run. Okay. And we can compile and run this by make q more low x. Again, PS, so we have these processes with the default priority 3 because we have PS loaded by the cell, okay, by exact, so the priority is 3. Okay. And now we run the full program again. We created say 2 full processes in the background, and now you can see that we have 2 processes with the runnable and one running with same priority 10. Okay. The parent is free, okay, but they are snipping. Okay. Now suppose we change this process that has process ID 10 to high priority, so 10 to, oh, it's too late. Yeah. Let's try again. Let's exit together. Let's do it again. Yes, now we changed the 21 to high priority using nice 21 to say 8. So you can see that 21 is always running. 21 and 28. 21 is always running. So because it's high priority. And just to review our full program. So the full program basically the parent creates a child that has the default priority 10, and instead of execute wait, that means it goes to sleep. So that's why you can change the child's priority and change the high priority also works. Okay. So there's a simple policy for priority scheduling. Okay. So you can try it yourself. Okay. Thank you. Bye bye.